So let's get into it. We have been discussing modeling for a while. Multiple interpretations of the model, how do we use it, the like. I was talking to Valentin and I said, I like the way you emphasize why do you want the model? What is the question you're trying to answer? And actually that's one of the big things for us. For us, in particular, because we are trying to put together how formal methods, formal analysis actually will use the models to answer questions. So we always look at the models from the question point of view. And the question will tell you what you need to model and how you're going to analyze that to obtain the answer. But it's not about that we are developing all the analysis ourselves. There are multiple domains that have been mentioned in the past as well here that talks about different, I would say, areas of expertise, different analysis domains as we call them. That, for instance, to talk about some of them, right? We have schedulability. That was part of my PhD, right? So I work on developing models for schedulability, timing guarantees. But there are models for instance, model checking, models for stability control theory, models for battery scheduling and thermal runaway. All of these models kind of use parts of the design that we have, the design document, in this particular case, the model, and we'll get information from that, figure out, do some analysis and figure out particular answers. Will I run into the thermal runaway? Will I meet my deadlines? Will my system be stable? All of them kind of have, go after this single authoritative source of data, right? So now we're calling it data. But the problem is that when we have all these interacting with each other, all of these models create abstractions. And the abstraction is basically not the whole thing. We were talking about that a model actually is a lie, right? But a useful lie. Now, when we talk about analysis, it's even a worse lie, right? Because, for instance, when I develop models for timing, what do I care about the software? I only care about what is the worst case execution time, what is the turn it takes to execute. Do I care about the value that is being produced? No, I don't care. It will finish on time. With the wrong value, well, I don't care, because I abstract away, right? Of course, there are other models about values. Model checking will take care of that. There are models about what is the effect on the physical system, on the physical environment. Will that be stable? That's another model for that. All of them make abstractions, right? So for instance, when we have model checking, they make sure that the value is correct. I remember I was working with a model checking guy at the SEI. We were working with a drone and say, yes, I'm sure that the drone will turn away from this virtual fence we are creating. It calculated the right value, but it took so long to calculate that it was outside the virtual fence already. Like, that's not enough. So whenever we are dealing with a physical systems, cyber physical systems, that we need to make sure that the values are correct, the timing is correct, that the effect on the physical environment is correct. All of these are different aspects that need to put together. So given the abstractions, they make assumptions to make them correct. And they provide guarantees. So this is actually what we do when we kind of create an argumentation, a model that combines all of these things together. And from this realization, over the years, we have created what is called an analysis contract. What exactly is the model assuming? What is the analysis assuming that the model kind of exhibits? And the assumptions can be made, we need to verify those assumptions. And you see these as functions because they were implemented, for instance, in a particular tool that we created. These are kind of implementations, for instance, in Python, can be implemented in Python. But then we create also guarantees. And these, you can see a very funny way to express the guarantees. This is because it's a formal way to put it in SMT. Don't worry about the way it's expressed, but it's a guarantee. I'm saying that I'm making sure that the worst case response time will be less than the latencies that are specified, right? It's a very simple way to put it. But part of the deal is we created this framework to make it what we call a symbolic analysis refinement, right? Assurance refinement. And the idea is that we want to start very early on when we make architectural decisions. We can start judging this, right? Are we kind of creating the proper replicas? Are they going to be independent? But once we get and put more information, we need to make sure that the assumptions that we are making and analyzing at a high level are going to be met as we keep refining, right? We create processes, we create threads, and we say, well, we need to make sure that they meet the real-time requirements. Okay, so what is the priority assignment? Oh, we don't have priorities yet. Fine, we will delay that, but we need to make sure that just priorities will exhibit rate monitoring. So those are kind of the way to think about the refinement side of things, right? Very formal, we can actually execute this. We can figure out whether the assumptions can be met. We can already, for instance, if we don't have enough information to figure out whether the assumptions can be met, we can figure out whether we don't have contradictions already, right? And that's part of the app. With this, we're able to create what we call the argumentation, right? We have different claims for the verification, and these different claims can be connected to analysis that will provide guarantees. So this claim will say, well, I have timing guarantees, reliability guarantees, control theory guarantees, right? You connect that to an analysis, you get evidence. I'm putting ADL. ADL, don't worry too much, is yet another architectural language, was created at the SCI, but can be any of these definitions as soon as we have good semantics to express what we want. These will have assumptions that can be verified again with another analysis if we want, but it could be just verifying values. That's also possible. Or if we don't have enough data, we can defer that, what we call a proof obligation. And that's kind of the mindset that we had. And you can see this, well, this is kind of the way we formatted that in text, if you will. The contract has particular queries. What exactly are we obtaining from the models? What are my assumptions? Do I have enough data to run this? What is the analysis that is going to create, and the like. And that's actually, I'm kind of getting ahead of myself a little bit, right? But the assumptions, the constraints that must be valid for the analysis to be exhibiting the proper values, the analysis itself, the guarantees. The implementation, as I mentioned, is the formalization with a particular formal tool, I will say. It's a way to model constraint satisfaction problems with satisfiability models theories. And this allows us to not only have what are the questions I'm going to be asking, what is the tool or the analysis that I'm going to be doing, what I'm going to be using, the assumptions, but are they consistent with each other? This allows me to do that. And allows me to do that automatically. Once I express this, I call the tool, and the tool will run it and figure out whether I get contradictions. It will tell me what contradictions I get. If I don't have contradictions, it can tell me, yes, I don't have contradictions, but you have not specified these things. But it will also tell me, right? Part of this particular effort is to be able to make it automatic. Once I have my my argumentation, if you will, my argument, that's it. I can start kind of executing this. The idea is also to be able to reuse these contracts, right? So I have a contract. I know what the guarantee that contract will give me, and I know what assumptions they need. I just need to connect it to the argument of the current system that I want to evaluate, right? Let me see if, I think I have been mentioning all this all along. One of the philosophies of this particular approach is to exploit the knowledge of the scientific domain. There are two ways to think about these models. In reality, all these scientific domains have evolved in parallel to each other. And they have evolved because the complexity of realities, or the reality is so complex that we need to divide and specialize in multiple I will say, communities, if you will. So for instance, when I publish in the community that I typically make my contributions real-time scheduling, I go with these guys and say, yes, timing is king, don't worry about values. As soon as we guarantee the deadline, everything is fine, which is just a fraction of the reality. And sometimes I hear, for instance, even that say, well, the code is the ground truth. Code is an abstraction. Code doesn't tell me how long it will take to execute. It's an abstraction, right? It doesn't, we don't know how long it will take to execute until we put it with a processor. And we put it with an operating system with other threads around that, right? It doesn't tell me what is the reliability, right? So everything is an abstraction. We need to put them together to figure out what exactly are we asking and how do we get those answers, right? Let's see what I'm missing here. And well, the fact that we have different communities, and the idea is to say, we do not want to build a new abstraction to kind of get the answers. We want to exploit the knowledge that is already there. So we want to take care of or take advantage of the analysis, and the only thing we need to say is encapsulate it so that we can connect them properly. We can honor the assumptions that they make and use them together, right? To make it scalable as well, right? So we are not gonna prove the correctness of the analysis. We assume that it's correct. We just need to make sure that everything that is around and that it uses is properly taken care of, right? So for instance, examples, these examples will come from my own domain, that is real-time scheduling, to say, well, if I want to make sure that I meet deadlines, for instance, I have different assumptions to say the priorities assigned to the different threads that I have need to be rate monotonic. I'll explain this to you. Don't worry about the label, right? The periods need to be harmonic, another property. We don't know what it is. The periods and the deadlines need to be the same in order to use this particular analysis. If you want to use this, all of this must be true, right? So if we focus on only one of them, we can see that, for instance, harmonics means that a period is a multiple of another one. So you can see, well, 15 is not a multiple of 10, so we are violating already harmonic. So what do we do? The analysis will tell us, right? The execution of this argumentation will tell us, hey, these are not harmonic. There are two options. One is, if I can do it, if I can modify the period, I do and modify it, I go and modify it. But it's also possible that I cannot do that. But the analysis can give you alternatives. Say, well, if that's not possible, what if you use a different analysis that do not have that requirement? But is able to explore this kind of collection of analysis, if you will. As soon as we have the proper package, right? The proper package is actually this contract that we were discussing, right? That's the idea of the framework. So this, just to give you the intuition of what we are doing here, is we are kind of creating this argumentation out of these contracts that allows us to kind of connect the different kind of guarantees with the assumptions and how the assumptions are proven, and alternatives of how to prove different properties from different analyses. All of this has to, of course, I'm just exploring one of the domains, but you can do the same with, for instance, control theory. You can do the same with reliability. And the idea is to put together knowledge already coming from the different domain areas, right? And that's kind of don't worry too much about this, but it's basically how it looks. It's basically a specification that we can translate into a formal constraint satisfaction problem. Now, we have been mentioning before, I mentioned, this particular implementation was kind of started with an ADL backend when we described the architecture. But of course, we created a query language that actually can be connected to any type of a specification. So we recently created a connection with SysML-v2. There is a translation between SysML-v1 to ADLs where we can kind of consume that as well. We're trying to see whether we can do the connection directly, just to have a better way, a simpler way to do this. But in the end, what we want to be able to do is, like, from this query, we connect all these analysis contexts that we were discussing before into an argumentation that will allow us to satisfy claims, typically certification claims, right? That will use, of course, behavioral models I mentioned for instance, schedulability, MATLAB, control theory, differential equations, all that. So how have we used this model? We created a working group called ASER, Assurance Evidence for Continuously Evolving Real-Time Systems. It's a mouthful. Don't worry, it's a group like any other group, just we have a shared interest. In the group, there were people from the FAA. The chief advisor for software was with us. Very interesting how to use these approaches to improve certification. Right? If we are able to transform this and get the support of formal methods and tools, hey, that would be great. Right? And he said, well, okay, so we have been thinking about this. You guys have this particular approach and tool. Let me give you a problem so that we can test it. So the problem is an incident that occurred in 2020 in Taipei, an Airbus A330 that actually we have all flown. So when it was landing, it kind of bounced off a couple of times, right? So, well, that's just everybody has experienced that. But the problem is that because of that bouncing off, the aircraft kind of suffered for a triple computer failure. Like, what the heck is going on? It was an incident. It means no accident, no crash, but it was almost around the runway, right? So we got the incident report, and we say, do we have enough information to create a high-level model and apply analysis to that, and find out what are the assumptions that are broken, if there is any. This is the high-level picture of the model. And the idea, these are kind of patterns that if you have interacted with avionics systems, you will recognize. This pattern is called self-checking pair. So there are two functions, two computers that calculate the same value, and they are supposed to be comparing with each other. And if there is a difference, they say, hey, something is off. I fail over to the next guy, right? These are control systems, so they control two things. They use the pedal of the pilot to control the rudder if they are in the air, or the wheels if they are on the ground. So they have a sensor, the weight on wheel sensor, to find out whether they are on flying or on land. And of course, what it happens is that all three of them read the weight on wheels and also get the input from the actuator that is the pedal. So what happened is, of course, if one fails, the other one fails over until it goes to manual, if you will. And that is exactly what happened. Why? Because they have independent sensors, right? They decided to put independent sensors to keep the independence of failure. And the geared weight on wheels, right? One way to explain this, what they call channel asynchrony, is that all the COM sends one state, for instance, that they went on the ground, while all the MONs sense that they are wet in the air. They were calculating different values where they were supposed to be calculating the same value, and wherever they compare them against each other, of course, they were incorrect. This is just one of the variations that can happen. I mean, it's not exactly this variation, but the three primaries have that discrepancy. And they discovered that they have that discrepancy, right? And of course, you say, well, I mean, so isn't it obvious, right? We were discussing that the models are also communication devices. In reality, different teams take care of different aspects of the system, and some team was probably working on how to think about the reliability, the availability. Others were thinking about integrity, that is the self-checking pair. Others were saying, well, if this thing is already doing the control of the rudder, why don't we make it also the control of the wheels? Well, that level of complexity, the level of miscoordination, they did not communicate assumptions. That's part of the problem, right? So obviously, well, I mentioned this. We use different analyses. For instance, we use end-to-end timing analysis with rate monitoring priorities and things like that. Fault tree analysis for the availability. So we apply this analysis and we say, what are the assumptions? We have also assumptions about the integrity of the self-checking pair. The assumption, of course, that you may be already guessing is that they should have the same input to calculate the same output. Isn't that obvious? Yes, it's obvious, but they assume, well, why it was not the same input? Because they were not sampling at the same time. So there is a little bit of, you can see the connections now, right? You say, well, calculation of values, simple. I can even give you a guarantee from a model checking and say, this calculated the right value. And it still be wrong because it was at the wrong time. There are connections between and interactions between different, I will say, verification domains, right? If we don't capture them, we don't verify them, we have problems. Of course, I mean, analyzing multiple, this is the original design, don't worry about this. This is the pictorial view of in ADL. They have independent sensors, right? The COM and MON. COM is commander, MON monitor, right? I'm just exploring one of them. But we explore different ways to think about how to make them receive the same value, because that's the assumption that was broken, right? The simpler one is to say we need to ensure that there is, in the sampling jitter, the sampling is at the same time means typically the difference is called jitter. So if we want that exactly at the same time, we call it jitter 0, right? Oh, sorry. Jitter 0. But in this case, of course, it was very difficult to think about jitter 0. So what we decided is modify the architecture so each pair has a single sensor. In the end, if the sensor fails, the whole pair fails. But if one of the elements, one of the two fails, also the whole pair fails. So it was a fake failure independence. So we decided to go after that, after exploring a few other options. It's a simple check. We were able to check that the assumption was corrected and that we were able to avoid that problem. The new architecture, just same sensor, done, right? Now, a few observations, final observations if you will. You can go download the tool, play with it. There is an expansion of the tool there as well. This is just, we have been exploring this area of analysis contracts for a while. Way to implement this, how to make it possible to automate, take advantage of the analysis of the formal methods that have evolved and have been making themselves more scalable. We are not done. I will say we have one way to capture this. We are trying to integrate also, for instance, these are formal arguments, but we are trying to bring also informal arguments. It means what happens if I have a very smart expert and the expert say, perfect, it works. Or what if I can mix also test that is not exhaustive, but it's a test. So all of these have been evolutions that we have been making. We have new results being published about these mixtures, a new agenda to continue our work, right? And I'll stop here and answer questions if there's any.
Thank you, Dio.
Thank you.